All right. We have to do one more example, and that's the stored platform. Okay. So the 6 SPS, otherwise also the stored golf platform. Okay. I want to do this example because this is one case where you don't have to do this. Okay. Remember I said that when you have spherical joints and there's nice symmetry, right, you can exploit these features to do the analysis in a much more straightforward way. Well, this is such a case. So let's, I think we can draw a picture here. Okay. Okay, so let me just draw one leg. Spherical joints, and here's the leg. Okay, and let's draw the frames. So here's my fixed frame, here's my end effector frame, moving frame. Okay, so we're going to do a differential analysis of this. Okay, we're going to do it in a different way. Okay, we're going to do a static analysis of this, statics. Okay, and get the Jacobian that way. So let's see. First thing we need to do is let's define some vectors here. Actually, before we define the vectors, okay, let's write down the static governing equation for static analysis. Okay. So using the same virtual work principle, okay, we can also make the argument that for this closed chain, it's the same relation. Okay, tau equals J transpose F. Okay, so tau, these are the input torques. Okay, so that would be the torques here. Okay, F is going to be the force at the end effector. Okay, the spatial force. So in this case, it'd be the three-dimensional linear force and the three-dimensional moment. Okay, so this also holds. Okay, from the same virtual work considerations. From same virtual work principle. Okay. All right. So in this case, we're going to use the static perspective to try to get J. Okay. All right. So to do that, we need to make a couple definitions here. So let's see. Each leg. Okay. So what we're going to do is we're going to do a static analysis of this rigid body. Okay, so this is something that we all learned in dynamics, right? Free body diagram, draw a rigid body, draw all the forces on it, okay? Add them up, and if it's in statics, set them equal to 0, right? So the forces acting on this rigid body are where? Are through the legs here, okay? So there's a force here, and there are forces at the, okay, other legs. So let's call this vector F, well, F leg I, so Fi. Okay. All right, so Fi, this is the force applied by leg I. Okay. And I'm going to write this in the following way. I'm going to write it as omega I hat. So omega I hat is a unit vector, okay, in the direction of the leg, times tau I. Okay, so tau I is the input force. Okay, so it's the force magnitude. Input force magnitude at leg I. Okay, and omega hat I is the direction. Okay, so it's, let's say it's unit length. Okay, so that's the force. What's the moment generated by this? Okay, moment. Let's call it m sub I. Okay, it's the moment generated by f sub I. Okay, so that's just, well, we have to make a definition here. So that's, let's use the fixed frame. So we need to define this vector. Let's call it r sub I. Okay, so m sub I is Ri cross Fi. Okay, that's the moment associated with force Fi, written in terms of the fixed frame. Okay, now rather than write it this way, I'm going to write it in a slightly different way. Let me define another vector from the fixed frame origin to that joint. Let me call that q sub I. Okay, so that's my vector q sub I. So since Ri, we can write this as vector q sub I, right, plus this vector corresponding to the leg. Okay, so the direction we said is omega I. And leg length, let's call it s sub I. Okay, so s sub I is the leg length. Okay, we can put that in here. Okay, and you can almost get this by inspection. So m sub I is Ri cross Fi, or this crossed with Fi. So it's Qi cross Fi, okay, plus omega hat I Si cross Fi. Okay, and now replace Fi by omega I tau I right here. Place there. So here we get Qi cross omega I tau I. Okay, and now you might think it's a little weird, but actually it's not. Let me switch the orders. It's minus omega I cross Qi tau I. Okay, plus omega I Si cross omega I tau I, omega cross omega, 0, 0. Okay. All right, so here's my moment equation. Here's my force equation. Okay. Now let's write the following. So statics, okay? So assuming static equilibrium, sum of the forces equals 0, sum of the moments equals 0. Okay, we want to write it this way. I from 1 through 6. Sum of the spatial forces, F sub I. Okay, let's write it out here. Okay, this is summation from 1 through 6. Okay, let's write the moments first. Here are the moments. Minus omega I cross qi. I guess. And then down here we have omega I, tau I. Okay, this has to equal 0. Actually, well, hold on. Actually, we don't want to set 0. We want to use this. We want to use this, okay? We want to use this. All right, so hold on. Let's calculate the spatial forces. Okay, so now this we can write as what? Minus omega 1 cross q1 omega 1 minus omega 2 cross q2 omega 2. Okay, and we have 6 of these columns times tau 1 up to tau 6. Okay, so those are the spatial forces. Okay. All right, so this is going to be my F. Okay, in this equation. So what I've written there is essentially F is equal to, now in this case this is 6 by 6. Okay, so F is equal to J inverse transpose tau, okay, from our static equation. So what do we know? We know that now that in fact it's this matrix here. Okay, this matrix here must in fact be J inverse transpose. Okay, so if I want the Jacobian, what I need to do is I need to take the inverse transpose of this. Okay, so for the Stewart platform, for the 6 SPS, we can in fact get the Jacobian by taking the inverse transpose of that. Okay, so let's write it. So it's minus omega 1 cross q1 omega 1 omega 2 minus omega 2 cross q2 omega 2. Okay, it's this inverse transpose. All right, you see this? Looks like what? Looks like a screw. Right? It's the screw corresponding to leg I, but it's switched, right? Switched. Okay. All right. So this is again, it bears repeating. When you have, special features in the manipulator, okay, this type of analysis can get you, the Jacobian in a much easier, cleaner, simpler way. All right. So with this, let's now